So sometimes with area between curves, it works better to integrate with respect to y than integrate with respect to x. This is that kind of situation. So let me show you where we're asked to find the area between these two curves, x equals y squared minus 4y and x equals 2 minus y minus y squared. Okay, you can see first of all that they've got x in terms of y rather than y in terms of x. And these are two parabolas like our previous example of two parabolas, but they're parabolas facing this way. So if I graph this, let me see if I get this right. One of them goes like this. You can see they both go through 0, 0. One of them goes like this, and one of them goes like this. So this guy is 2y minus y squared, and this guy is the other one, right? That's y squared minus 4y. So if we try to do this with respect to x, it actually would be a huge mess, okay? First of all, I mean, we could do it if we wanted, but it would just be really long and arduous. First of all, we're looking at the top curve minus the bottom curve. You actually have three different regions here, because in this region over here, it's this curve, the top minus the bottom is the same curve. In the middle region, you've got that top curve and that bottom curve, so they're different. And over here, you've got the other curve, top minus bottom. And how are you supposed to get top minus bottom from the same curve? Well, what you would have had to do would be, we'd have to solve this for y in terms of x. So in both of those cases, we would have to complete the square. There would be a square root. And these funky regions over here would be like the top, the positive square root minus the negative square, whatever, minus negative square root. Anyway, it would be awful. Luckily, instead, we have another option. Because remember, in the previous video, we took an approximating rectangle that was up and down like we're used to. But here, with everything written as x as a function of y, we can take an approximating rectangle that is horizontal. Right, so really this is what we want to do, right? So this is dy, right? We're going to want to take then the integral with respect to y. And just like before, and we'll call it CD because before we had A, B, but whatever those points are, they're points in y. Before we want to take the bigger curve minus the smaller curve. So here it's the same thing. In this case, of course, bigger means more positive, so more to the right. So you want to think about this as the curve on the right minus the curve on the left, if you're going to be integrating with respect to dy. So I like to write it as x right minus x left, and then dy. Okay? So all your variables will now be y. Your limits of integration are also going to be points in y. Okay? So when we set this problem up, we're going to have to find these points of intersection. And what we're going to really need to find, okay, obviously this one's 0, 0, right? But we're going to need to find, we need the y coordinate of that point, which is what you get. We set it up that way, but that's pretty much fine. So let's do that. Let's do it. So the curve on the right here is this guy. That's this one, 2y minus y squared. And the curve on the left is this other one, y squared minus 4y. And we have to figure out what these points of intersection are. So I'm just going to do that down here. I'm going to set these two things equal to each other. Let's put everything on this. This is 0 equals 2y squared minus 6y. Okay, so 0 is 2y times y minus 3. So indeed, it does come out 0 is your bottom. right? And the top is going to be y equals 3. Right? I don't know what the x coordinate is, and I don't care. I mean, I could figure it out, but I don't care. But because my variable of integration is y, my limits also, they have to be the y coordinates. Which, as I said, we got it automatically the right one. So that's fine. That's what you should get if you're setting it up that way. So let's see what we have here. Integral from 0 to 3 at 6, right? 6y minus 2y squared. So 3y squared minus 2/3 y cubed. Evaluate from 0 to 3. So 3 times 9 minus 2/3 times 3 times 9. Bump, 3 9 minus 2 times 9 is 1 times 9. So the answer is 9. Oh, I forgot to write minus 0 because I did it in my head. But yes, don't just do it in your head. But definitely remember it. Always remember that lower limit. Even if it's 0, don't forget. All right, well, so sometimes this is better to do with respect to y. Sometimes it's better to do with respect to x. There are some unfortunate situations where you have to break it up no matter what. There's not one better way than the other. So let me do one like that. That will be my last example here. So we have, where to go, on this down, y equal 1/4 x squared, y equal 2x squared, x plus y equal 3, and we want positive values of x. All right, so if I draw this thing, all right, y equals 1/4 x squared, that's like a low guy. Y equals, maybe I should have made that a little bit even lower. Maybe I'll make it bigger. Here, 1, 2, right? Maybe some points would be nice to make it look good. Right? This guy. And then y equals 2x squared. He's doing that. Now this is just going to be y equals 3 minus x, so it's y equals negative x added up to 3. So here's 3, right? So I go like this. Okay. So what they want is this region here. One thing, because of course it has the 3 different curves and it's kind of messy, I have 2 options, but there's no way of getting around the fact that I'm going to have to break this region up into 2 separate regions. So if you look at it, how are you going to do this if I'm going to integrate with respect to x? I can break it up like this, right? Because this first region, I've got this curve minus that curve, and in the second region, I've got this curve or line minus that curve. So that's my one option. My second option, though, if I want to do this with respect to y, I would break it up like that. So on my top region, I'd be doing this line minus this curve, and on my bottom region, I'd be doing this curve minus that curve. Okay, let me actually write what these curves are. So those are my options. I'm probably just going to stick doing it with respect to x, because then I don't have to have square roots, but I mean, it's not like it's going to be pretty much the same amount of work either way. Okay, so if I think about it, doing it with respect to x, I've got one region here and the second region here. Yep. And I need to figure out what all these points are. So I got to do more work here than in the previous examples because like I have 3 different curves and I have to figure out what's going on. So for my first region, I've got the 2 parabolas, but where it stops is this point. That's the point that I need to find. That's the point where this parabola hits that line. So my first point is going to be this guy, 2x squared equals 3 minus x. So I need that particular point, right? So, what do I have? 2x squared plus x minus 3 equals 0. So I've got 2x and x. I want the 3 here and the 1 here, right? And it should be 2. Wait, is that right? What did I just do? This is minus 3. This is plus. Yeah, no, I want a plus here and a minus here. That's why I have the minuses messed up, right? Because I want it to be 3x minus 2x, so it'll be 1x. Okay, so x equals negative 3/2 and x equals 1. Because all this goes on this other side, there's other stuff going on there. That's what my x equals negative 3/2 is. I don't care about that, okay? And these two, I already know that's at x equals 0. So for my first integral, I'm going to go from x equals 0 to the point that I found, which was x equals 1. Of course, it turns out this point is 1, 2. I can figure out the 2 just by plugging it into either of those equations, but it doesn't matter. Okay? And now, on that region 1, my top curve is this first parabola, my steeper parabola, and my bottom curve is this lesser parabola. Lesser, lower, smaller, I guess is what I'm talking about. Okay, so that's the very first region. So now I'm going to do the same thing for the second region. I know I'm starting from 1. Let's call that point 2. Point 1. Point 2. This looks like it's going to be at 2, but we need to check that, right? It's not obvious. But so for point 2, I'm going to take this curve and find where it hits this line. So I've got 1/4 x squared equals 3 minus x. X squared equals 12 minus 4x. So 6 and 2, right? Plus 6 and minus 2. When I factor. So yeah, there's a minus 6, but the one we want is in fact this one. We want the x equal 2 part, right? That's going to give me this point. Okay, so x is going to go from 1 to 2. And then on region 2, the upper curve is the line. And then the bottom curve is still the shallower parabola here. Okay. So basically, the way I figured all this out was 100% from the picture, right? I drew the picture, I figured out the regions from the drawing, and then I had to figure out the points from the drawing. So without a picture, I really wouldn't even know what to do. So the picture is very important. Okay, now the rest of this is easy, right? This is an easy integral, so I'm going to barrel through this real fast. This was 8/4, 7/4 x squared dx. There's nothing to do. I'll just rewrite it. So you're doing that one. So this would be 7/4 times x cubed over 3 from 0 to 1. And then I've got this, this. Anyway, when you evaluate all that, I actually did this somewhere. It turns out nice. It turns out to be 3/2. That's what I got. Anyhow, so you don't all have to watch me do arithmetic because that's